Ladies and gentlemen, thank you for standing by. The conference will begin shortly. Ladies and gentlemen, thank you for standing by. Welcome to the FHWA and PPRA webinar series on pavement preservation. At this time, all participants are in listen-only mode. Later, we will conduct a question and answer session. Instructions will be given at that time. If you should require assistance during the call, please press star, then 0. This conference is being recorded. I would now like to turn the conference over to your host, Jason Dietz. Please go ahead.
Thank you, Sandy. Welcome, everybody. Thanks for joining us today. We're very happy to provide you a webinar today on a webinar series under pavement preservation through the Pavement Preservation Recycling Alliance as well as Federal Highway. Over the past few months, starting back in February, we provided some webinars each month, and hopefully if you had a chance to sit in on them, or if this is the first, at the end you'll see one of the things you can download is a little flyer that will provide you some further details of some upcoming webinars and some of the recordings that we have done in the past. So again, welcome. Before we get started, I just want to say a few words about pavement preservation. You know, we all know it's a sum of strategic activities performed to preserve our investment, especially in the times that we are today. We want to preserve our roadway. We want to enhance our safety. We want to extend our pavement life as well as improve our functional performance and contribute to increasing user satisfaction. A key principle of pavement preservation is keeping good roads good, so that's the importance of why we're here today, and we really welcome you. With that said, we'll get started. I'd like to introduce you to our speaker today. His name is Dan Wegman. He's a PE. He's from Wags and Braun Intertech. Has worked with DOTs and local government agencies in several states with a pavement preservation, pavement rehab, and preventative maintenance strategies. He is a former Minnesota DOT construction and bituminous engineer and has over 20 years of experience as a private sector material supplier. Wegman provides the technical insights in respects to materials, construction, and implementation. I'd like to introduce now Dan Wegman. Take it away, Dan.
Thank you, Jason. I just want to start out with some of the questions that we had at the beginning that shows the familiarity that people have. We asked both with engineered emulsions and with emulsions, and I noticed that the responses are relatively the same. So that's good information to kind of help me tailor the presentation accordingly. Looks like we've got the vast majority of the people are beginner and intermediate, so we'll try to address your needs the best possible. So with that, I will go to the big screen here and begin. Again, my name is Dan Wegman. The topic is engineered emulsions, and I am presenting this through WEGS on behalf of Viability. So what we're going to do today is talk about the history of engineered emulsions. We'll get into some material basics. We'll talk about the applications that the emulsions are used in, and then cover probably the most important thing, which is performance and why they are the best rehab binder option when viable. Starting out with the history of engineered emulsions, here's kind of a timeline of the history within Minnesota, which is appropriate because that's where engineered emulsions originated and developed. And it started in the 1980s, and that was a time when there was several cold-in-place recycle projects going on, and many of them had issues, and the issues were primarily around, a little bit around placement and equipment issues, but a lot to deal with the performance of the roadway prior to the overlay going on top of it. What happened was there was a longer period of time that the roadway had to sit open in order for the water to leave the emulsion and prior to the overlay going on. And so what happened was the surface would ravel or deteriorate over that time frame, and it became a problem, especially in those jobs where it stretched out over a week or two prior to the overlay going down. And so what happened was they decided that they were going to maybe put a moratorium on cold-in-place recycling after, it was the late 80s into the 90s. So in 1998, a joint agency industry meeting was put together, and for industry, it was both the binder suppliers and the contractors in addition to their equipment suppliers. And so that meeting went a long way to really identify, responsibilities going forward in terms of making the process and the product better. And the contractors were charged with better laydown, which included improvements on equipment. The binder suppliers were charged with making a better binder that would stand up to the traffic and weather prior to overlay going down. And the agency was charged with kind of putting together contract administration and specifications to help that happen as well. So that was really the origination of the need for a better product. And it's not just engineered emulsions. It was overall a better process, including both laydown equipment and the agency's participation. So I was with Coke Pavement Solutions, Coke Materials at the time, and for CIR, Arlis Catamaris really put in a huge effort in terms of beginning the development of that. And in 2000, the first full-depth stabilized engineered emulsion project was placed in Chisago County, and we'll talk about that a little bit further. In 2002, the FHWA had a mandate that went out on recycling, which basically said that recycling should be a first consideration because of the environmental benefits that it offered as well as other benefits that it brought to the table. Much like many of the unfunded mandates that came through the FHWA, it really didn't stick in a lot of agencies. And so it was quite a bit of time for the whole recycling process and concept to get a lot of momentum behind it. In 2008, Minroad built cells 2, 3, and 4. They were constructed at the Minroad facility, and I will go in depth on what transpired with those cells and how that advanced the technology. And then in 2013, there was considerable performance data that had been gathered over the previous 10 or so years. And that really got the snowball rolling, got a lot of additional projects going, and use by multiple agencies increased just because of the performance that people were seeing. So as I said, it kind of all started in Chisago County, which is a county in Minnesota just north of the Twin Cities metro area. The road was County State Aid Highway 86. And in 1999, they utilized technology that was brought over from Finland. Finnish emulsion gravel was the technology. And Chisago County is home to many Scandinavian people. And so it kind of was a good fit. And the whole concept of emulsion gravel, Finnish emulsion gravel, was to have a very strong base and then put a very thin asphalt overlay over the top, like 1.5 inches, that's very flexible, so that the base is supporting the loading and the thin overlay is providing protection for that strong base. So you can see there on the left a picture after one winter of that finished gravel roadway. And the vast majority of the job, looked good. It was performing well. But there was about 5% of the project that looked like this picture, where significant distress and damage had occurred. And that really kind of resulted in the need for something to determine how strong and in weak areas be able to strengthen your base for that thinner overlay to perform. And that was really how the whole concept of an engineered emulsion in a base stabilization process originated. And so what happened was we went out and did a stabilization of that road, which is basically regrinding that pavement with the base and stabilizing that with an engineered emulsion, and ended up with a really good product. But there was things that took place in the interim there because of that 5% of the road that didn't have a very strong base, and we needed to understand that prior to that process. So I need to distinguish between base stabilization and subcut correction, because we did go out and do some pavement evaluation, coring, looking at the in-place materials in order to define what was going on in these problem areas prior to doing that base stabilization. As you can see on the right, the picture where we had areas where heavy clays were in that base material. They either contaminated that base, or it was a section that had that material in place previously. The county had picked this road because it was what they believe was their strongest base in the county. And Chisago County is a county that has a wide variety of underlying subgrade soils and a wide variety of different types of pavements, whether it be full depth, deep strength, or traditional aggregate-based pavements. And so what we need to do in these areas is to go in and subcut, correct, or dig out that clay material and put back millings from the project and other base material that's going to provide adequate strength, and that was done. And the thing I want to emphasize here is that upfront evaluation work is critical to the success of any type of stabilization you're going to do, and I'll emphasize that a few times going forward. So we'll get into material basics. And when you look at common asphalt additives for recycling, the three most common right now are foamed or expanded asphalt, what I call commodity emulsions, which is basically a cationic flow set emulsion, or engineered emulsions. And really, for those of you that are not familiar, a foamed or expanded asphalt is basically bringing hot AC out to the job, and it needs to be really hot. I mean, you're usually talking about over 300 degrees for that foaming process to function properly. And what happens is it goes into a chamber where water is sprayed with that hot AC, and that reacts violently and expands that asphalt, which is why it's called expanded asphalt, and that allows the coating to occur in a very short period of time. And so you've got that expansion chamber and what's called a half-life in order for that coating to occur. And so what happens is the fine aggregate in that base material gets coated, and a lot of people call it a spot weld, where those coated fine aggregate materials hold the coarse aggregate in place. So that's one type. And then the commodity emulsions, which were used prior to engineered emulsion, are just your typical tack type emulsions back in the day. But what was determined was that a lot of the tack emulsions were not formulated for mixing grade applications. And so until engineered emulsions came around, you really didn't know if you were going to get an emulsion that was going to provide you with good mixing characteristics for a stabilization process. And that's really what transpired into developing engineered emulsions, which is what we're going to spend a lot of time talking about today. So why are there emulsions? Asphalt is a semi-solid or solid at room temperature. In order to get that material to coat and to be workable, it needs to be in a liquid state. And that can be liquefied by heating the asphalt, which is the typical approach in hot mix asphalt applications. It can be done by adding petroleum solvents, which is done in cutbacks. And it can be done by emulsifying the asphalt in water, which are emulsions. Now, cutbacks were used significantly more than they are today back in the distant past. And the reason was they are very capable of making that asphalt liquid. In fact, they put in a lot of light ends that make that material very flexible, which means that it becomes very crack resistant, but at the same time it doesn't stand up to heavy loads or traffic quite as well. And so because of environmental aspects, the solvents basically can get up into the air, and because of the very flexible nature of it in terms of the increased traffic loading and heavier loads, cutbacks have been used substantially less now, and a lot of that volume has gone over to emulsions. So when we talk about emulsions, what is the definition of an emulsion? Definition of an emulsion is a suspension of small droplets of liquid in a second liquid with which the first liquid will not mix. In order to accomplish that and be able to handle it at air temperatures, we need to have it consist of asphalt, water, and probably most important is the chemical, the emulsifying agent, or that surfactant that's used in making the emulsion. And breaking occurs when the separation of that asphalt and the water occurs, and basically that asphalt then goes from a liquid that is able to mix and coat that aggregate material to an asphalt that is going to provide, the glue that holds it all together. And really an aggregate, when you think from an aggregate's perspective, an aggregate really doesn't care how the asphalt gets put into the system. But, with all these different ways of getting the asphalt there, there's a lot of things to think about in terms of doing it properly and what effects can the different material aspects have on the overall construction of the pavement itself. So upon curing, the residual asphalt retains all the adhesion, durability, and water resistance of the original asphalt cement. So like I said, the aggregate really doesn't care how it gets there, it just needs to have it there in order for the pavement to perform. So we'll go to our first polling question. Number one is, how many attendees suppliers do we have that make an engineered emulsion and supply it into their marketplace? Like it's going to be about 2/3 to 1/3, Jason.
All right, we'll broadcast those results.
So I think, that's good to know that we've got a lot of folks that are actually making engineered emulsion in attendance, and that's just a testament to the success that has had over time in order to get that to grow in the marketplace. Now we'll talk about emulsifying agents, which again is the surfactant active material or soap that is used in the emulsifying process. What that does is it keeps the asphalt droplet in a stable suspension. It controls the breaking time. It determines the classification of the emulsion, which we'll talk about further here. And typically you have two types, although there is actually three. You've got cationic, which is a positively charge on that material, anionic, which is a negative charge on that material, and then you also have non-ionic, which is a neutral charge. And with that, you have different types of curing times. You have rapid set, medium set, and slow set. Back when cutbacks were used, it was the same nomenclature, although they called it rapid cure, medium cure, and slow cure. And then you have basically a measure of relative viscosity. So I mentioned that commodity product, the CSS1 or CSS2, basically is a measure of relative viscosity with the 2 meaning it has a higher viscosity. And then the H at the end indicates that a harder asphalt is used. And we'll talk about selecting the base asphalt for making the emulsion a little bit further. So factors affecting that breaking or curing time. And I should mention here too that I'm kind of covering these fundamentals of emulsions relatively quickly. There has been a detailed webinar through this group that was recorded. And for those of you that want to get detailed information on the fundamentals of emulsion, I encourage you to go back and listen to one of the earlier recordings on that topic. So factors affecting breaking and curing, you've got weather conditions, temperature, humidity, and wind. Wind can be an awfully big factor at times. Water absorption into the aggregate itself. Typically, aggregate that has high moisture content going in, wet aggregate may help facilitate coating, but that in turn can slow the curing process. So you've got kind of double edges of a sword there that can help or hurt you depending on what your application is and how you're applying it. And then you have mechanical forces. So any operation that's using compactive effort or rollers to compact the material, you're also forcing water from that mix and assisting in the curing time with that activity as well. Surface area is often underlooked, but it's a very big, huge factor. Excessive fines or dirty aggregate accelerate breaking. That can be especially an issue with fast curing products like microsurfacing is a surface treatment that you could say uses an engineered emulsion because that emulsion is definitely engineered to provide a proper break based on the materials that it's coating. Mix designs are done up front to understand that, and we'll talk about those activities being an important part of the engineered emulsion process as well a little further in the presentation. And then surface chemistry, that whole aspect of being able to use chemistry to drive out moisture from the product is a huge factor as well. Some of the advantages of emulsions, they are much safer because the working temperatures are much less than hot mix asphalt and cutback applications. They are deliverable at a usable temperature. There's no need to heat them in the field. A lot of times with foamed asphalt, you get your asphalt out on a project after it's been on the road for maybe a couple hours, and it's not at a hot enough temperature for that expansion to occur properly, and it needs to be reheated in the field. And as we all know, when you reheat asphalt, you're basically aging it, much like you do when you look at the rolling thin film oven test with hot mix. You're doing some short-term aging that makes the asphalt more brittle and more prone to cracking. With emulsions, there are no solvents released to an environment, so they're environmentally friendly. They will adhere to wet aggregates, which is a plus in many occasions. They're less expensive. And there's a greater ability to control that breaking process with the surfactants and the chemicals that go into making the emulsion. They also have an attribute that often gets overlooked, is that just about all of them have a built-in anti-strip to provide better adhesion for the interaction with the aggregate itself. So now we'll talk about engineered emulsion. And before I start, I've got to give some credit to some of the people that were really key in developing the whole engineering emulsion product and process, and namely Bill Gruba with the Coke at the time. He's with Ergon now, and Peter Schilling, who is with Viability, spent a lot of time with the chemistry aspect of developing engineered emulsions. And Todd Thomas was the true pavement engineer that was tantamount to putting together the specifications and performance tests that are required to help define engineered emulsions in the various applications.
Okay.
Is there a question? Okay, so the engineered emulsion definition is a class of emulsified asphalt that is designed project by project rather than being a product specified with broad specification values. It is usually associated with mixed design methods in which the CR or SFDR mixture properties are determining the final properties of the emulsified asphalt. So what that means is with engineered emulsions, it went less to the actual material specification and more to the final product characteristics and engineering properties in order to define what that engineering emulsion needed to do in any particular application. So engineered emulsions have a lot of strengths, which include they add new unaged asphalt to the wrap, and I think that's extremely important. It was always the question of whether wrap was just a black rock or if that's some of that old asphalt binder on the wrap actually transferred over to the new mixture. And I think being a guy that used to lean more towards the black rock, I've learned over the years that depending on the materials you're using in the recycling process, you can get a lot of that old wrap to become effective in the process, and it's something that can be very beneficial in terms of the overall performance of the roadway. It gives a uniform coating on the wrap, and the difference between engineered emulsions and foamed asphalt really is that you're getting that uniform coating on all the aggregates as opposed to just coating the fine aggregates and having them hold those coarse aggregates into place. It also provides an old pavement more flexibility. When you think about the asphalt not going through a hot mix plant, not going through that short-term aging process, and then in a recycling application, it is deeper into the pavement structure, so it doesn't weather or age long-term nearly as fast. You're really providing that pavement with longer-term flexibility, which in turn provides greater crack resistance, has less distresses show up in the pavement, and results in longer life. It is also very good. You can ask anybody that's been around hot asphalt and has some spilled on them. It can be a very bad burn, and with the lower temperatures, it's much safer to work with. And then the key for engineered emulsions can be formulated for each location and aggregate. One of the things when they were being developed in Minnesota is West Vaco, the company that has now become Viability, came out, and I can't remember, it was just like dozens of 5-gallon pails of material that we grabbed from Chisago County projects over the first couple years, and they would take them back and formulate them and really understand to the level that you can apply engineered emulsions and know when it crossed over into an area where you had too much clay particles or other non-granular material where emulsions would not perform as well. So having that understanding was really key to successfully advancing engineered emulsions and making sure that they're only used when they're viable and that you're using some other binder such as Portland cement, lime, or some pozzolanic material when you get into some of those clay-type materials, and we'll talk about that further. Energy savings is a key factor and becoming a bigger factor as time goes on, ties right into the environmental aspect as well. And the next polling question is, how many attendees have used engineered emulsion on their projects? Okay, looks like falling right in line with that 2/3, 1/3 that we saw before. So that tells me that a lot of people are not familiar with engineered emulsions, and I think that I will talk about at the end a lot of opportunities to get yourself more familiar with these types of products and their ability to really advance the pavement system that you're either supplying or that you're either having contractors put in place for you to make your roads last longer. So a little bit about the engineered emulsion process. The first step is after you've done your homework in terms of looking at your roadway and understanding the materials that you're going to be dealing with, is to select a base AC, and basically you're selecting a PG grade, much like the binder selection process for hot mix. You'll be selecting softer base ACs for the northern climates and harder base ACs for the southern climates, and understanding that some states have both types of climates within their state, and you've got you've got to select that base AC accordingly. And so really keep in mind that in these applications, you also need to determine how far down in the pavement structure that material is going to be placed, because that affects your binder selection grade as well. Next step would be to assure compatibility with the aggregate. As we mentioned, that emulsions have charges to them. Most engineered emulsions that I'm aware of have a positive cationic charge to them, and certain aggregates, have more compatibility or less compatibility, and that's certainly true again with surface treatment type applications like microsurfacing, where the aggregate can be a huge factor in terms of how fast it sets up. With in-place recycling, it can also be a factor. One of the things that we're blessed with up in here in Minnesota is that the glaciers deposit a lot of really good aggregates, consistent material, and so going through that process of looking at compatibility of aggregates was pretty much a one-time deal, and now we can use that information to formulate going forward. And you're really formulating the emulsion itself for performance, and you're looking at that aggregate reactivity, you're looking at the mixing and coating characteristics, what kind of cure time you need, and that is both for having the material set up and be able to handle traffic, and also be able to get the material placed and constructed properly before it does set up. So both those come into play in terms of a successful project. And then adjusting to changing conditions. We all know that weather changes. We all know that the aggregate gradation can change over even the time frame of the day. A lot of times as the day heats up and the pavement gets hotter, the gradations can change. From the morning when it's cooler, you might have a coarser gradation that turns into a finer gradation. So not only adjusting to those types of conditions, you need to adjust both the emulsion content in some cases, and if you're talking about like a microsurfacing, you might be adjusting the formulation as much as possible on the fly as well. And the key here for in-place recycling is really that balance between strength and flexibility. You need that strength to handle your traffic loads. At the same time, you want the flexibility so that that roadway can remain distress-free, not have those cracks that allow air and water into the pavement structure, which cause further deterioration and then leads to a shorter pavement life. And so the thing that engineered emulsions really do is provide a really good balance between strength and flexibility for the person using the material on their project. Okay, if there is not any questions, we can move on to the key component of applications and where to apply these different engineered emulsions. So the two main places that they're applied in pavement rehabilitation is cold in place recycling. You can see on the picture on the left that it's a picture of a cold in place recycling train where the tanker truck in front is supplying the asphalt through a line that goes past the milling machine to the crushing unit and then gets mixed in a pug mill where the emulsion is mixed with that crushed milled material and then remixed and placed right back down on the roadway. And when you think about this process, you're using 100% wrap because it is a partial depth process. You're not going all the way through the pavement structure. And the reason for that is you need to support that heavy train as you're going down the road. So if you take too much of that pavement structure off, you can end up breaking through the pavement and causing problems with the laydown. I have to say that there is another process called a single unit cold in place recycling process now where you can use a piece of equipment that looks much like a reclaimer and not have the big heavy train and be able to place it that way. You get a similar result, although the train provides a lot more controls in terms of maintaining the proper gradation and actually allows you to have more controls on the volumetrics as well. And on the right, you've got full depth reclamation, which basically is using a reclaimer where that when it says full depth, that means it goes all the way through the pavement structure and into the base, and you're mixing that wrap material with the uncoated base material underneath and getting a material that you're going to coat with the binder, and that is done through the reclaimer. An emulsion package is put into the reclaimer and it's actually sprayed in that mixing chamber in the laydown process. So when you look at cold in place recycling, the definition of that is an economic or eco-friendly in place pavement rehabilitation process performed without the use of heat, and it does retard cracking. As far as it relates to reflective cracking, it takes much longer for cracks to come up from the bottom through that process, and that's an aspect we're going to talk about both CIR and full depth reclamation, is that that whole ability to keep cracking from finding a pathway through that stabilized material to the overlying surface material, whether it be pavement or a surface treatment. As you can see here, it is a partial depth process where it doesn't go all the way through the pavement structure. It just goes partially through, and typically you're putting at least a chip seal or a thinner overlay on that. You do get structural benefits from the cold in place recycling. It's not to the level of a hot mix, but it is significantly more than a ground up base, and you can utilize that in terms of reducing your overlay thickness, which makes the whole process more economical in the overall picture of it. And then the full depth reclamation, as you can see here in the pictures, it is a full depth process where you're actually getting through the pavement structure completely, and you're mixing with that underlying base. And there's really three processes, which are mechanical stabilization. A lot of people call that pulverization, and that is just basically going in and grinding up the pavement, combining it with the base material, and creating a new unbound base through that process. And then you've got chemical stabilization, which is utilizing some type of pozzolanic material, whether it be fly ash or cement or lime, and that typically works really well with bases that have been contaminated with clay particles, organics, or non-granular material. And then bituminous stabilization, which would include both asphalt emulsion and foamed asphalt. And then in addition to that, in recent years, the combination of two or more, usually it's maybe a combination of two of these, would result in the process where you would use a bituminous stabilization in combination with a little bit of cement, or more like a belt and suspenders approach to an overall stabilized material. So keys to success and really understanding how to apply the proper binder to the material that you're going to be stabilizing. And really some really fundamentals here can help in making that decision. There's also a very good reference document, which I'll show you later, in terms of determining what your best binder is going to be for the material that you're going to be working with. But here I just want to say that when you've got base materials, you can have a granular material and put something that's going to be more flexible on top of that to avoid cracking from occurring. And that flexible material will probably be more prone to rutting as opposed to a very stiff material, which can be more prone to cracking. But with a stiff material, you're really looking at providing a bridge or providing a structure over underlying base, contaminated base, or subgrade material that typically can be pretty strong when it's dry, but is very weak when it gets wet. So you want to be able to put a bridge over that so it's got enough strength to be able to withstand the weakness of the underlying material if it should get wet. And so if you look at the different products that can be applied over that full spectrum of stiff versus flexible and granular versus clay or organic material, I've kind of put the products that kind of fit across that spectrum, with cutbacks or road mix material being, to the far left. Those are very flexible materials that can be used, but again, they, in some cases, if you've got heavy loading, can be too soft or too flexible and can have rutting occur. Engineered emulsions is really that good balance between stiffness and flexibility, and that really provides you with kind of that middle of the road action in terms of overall performance. And then foamed asphalt and lime, you're progressing more to that stiffer material. As you get to fly ash and cement, you can get very stiff, and you really need to kind of monitor how much of that material you're putting in so you don't get it too stiff, because if you get that base too stiff, that will eventually crack up, and that cracks will reflect up through the pavement structure as well. So you should have a upfront design procedure utilizing those materials in order to make sure that they perform properly, and select the compressive strength is the performance test that they use appropriately for the loading that roadway is going to have. And then I've got proprietary products that I kind of skipped over. And proprietary products, there's a lot of them out there. A lot of them have their own not really even a design method, their own formulation. They tell you what application rate to apply them at. They tell you how to use their product, and then basically you're just going with that material supplier or manufacturer's advice and hoping that you get the product that you're looking for. And there's a lot of them out there. There's a lot more coming out, and what I can say about those is without the upfront performance testing, without the upfront mix design, you've got to really kind of do a trial by error and hope that you've got somebody that really knows what they're doing, because some of the products, in my experience, don't really stabilize. They don't really bound the material together. They can provide some stiffening action, but they don't bind the material into a bound base, and I'll show you why that's so important when we get into some of the more performance aspects. But be careful when you're using proprietary products. Make sure that you understand what their capabilities are and have discussions with the material manufacturer that's providing them, and make sure they understand where they're being applied and what to expect from those. I would recommend getting some type of a warranty when using those products if you're not familiar with them. On to performance. When we talk about performance, that's really the bottom line when you're using any type of a binder or application material, is how is it going to perform in the road itself, and that's going to dictate whether or not use gets increases, decreases, or stays the same. And so what I've got here is a case study of 2 county roads, and the reason I thought this case study is really good is because it was early on in the CIR process where this came up, where 2 adjoining counties had a connecting road, and the road was pretty close to being the same type of structure, and the counties had different opinions on what they were going to do to rehabilitate that road. And so based on those decisions, they came to different processes to use in that rehabilitation with very significantly different results. And it really was the beginning of expanded use of cold in place recycling because of the performance differences that were seen on this early project. So there's 2 county state aid highways. County 2 pavement was a 5-inch bituminous pavement over a 12-inch aggregate base, and that abutted a 2-mile portion of the County 1 project, which was 4 to 6 inches of bituminous pavement. It was variable thickness, which can be important in the process selection. It was an older pavement that had been overlaid a couple times and had 9 inches of aggregate base. So really, when you look at it from a pavement structural standpoint, they're pretty close to being equal. And so, as I said, that County 1 had a variable thickness road, and so they went out and did a bunch of cores and looked at what that thickness was at the time, and this is many, many years ago. Now it's much easier to go out and use ground penetrating radar to kind of understand your pavement thickness variability and be able to get a much better defined information of how that pavement thickness varies over the length of the project. But in this case, the cores kind of came out showing that 4 to 6 inch thickness, and that kind of fits with cold in place recycling in that typically you're looking at a 4-inch partial depth process where cold in place recycling is applied, and that allows you with material to stand up to the equipment that's going to be used in that cold in place recycling process. So I mentioned the importance of doing upfront evaluation of the road. They looked at their road and looked at the strength. It had a 9-ton rating, utilizing the FWD, falling weight deflectometer, to determine that. It had good ditches in place, and it appeared to be draining adequately. One of the major considerations for that county was that the performance of their overlays throughout the history of that abutting older pavement, that cracks had propagated through the overlays at a rapid rate, and they had used CIR in similar situations which had produced better results on other county projects. So they're really looking at that as a potential option. So in the end, kind of cutting through this pretty quickly and getting to the end result, County 1 chose cold-in-place recycling utilizing an engineered emulsion and recycled 4 inches of that original bituminous pavement and surfaced it with 3 inches of new hot mix on top. They did install drain tile to further aid that drainage on the roadway. And County 1, with that option in 2004, went back and measured the cracking in 4 years later in 2008 and had only 8 low-severity transverse cracks within the first 0.8 of a mile on that roadway. And when we say transverse cracks, they very well are probably low-temperature cracks that occurred from the top down as opposed to load-related cracks which occur from the bottom and work their way up. And so when you're selecting a cold-in-place recycling process using engineered emulsion, you want to make sure that you select a good PG binder that's crack resistance on top too to avoid any of that top-down cracking that might occur. County 2 chose the traditional standard rehabilitation at the time, which was a 2-inch mill and overlay. And they did that work in 2005 and then added a seal coat to it in 2006. They went back in 2008 after 3 years of performance as opposed to the 4 years of performance on the engineered CIR product in County 1. County 2 ended up with over 300 low to moderate transverse cracks and numerous longitudinal fatigue cracks within the first 0.8 of a mile. And so you can see a huge difference in performance in those two projects, and what that translates into is basically life of the roadway. And it's not just a one-time performance measure. Over the years, counties have gone back and they've seen significant crack reduction utilizing the cold-in-place recycle process as compared to the traditional mill and overlay process. You might pay a little bit of money, extra money up front to do it, but you're going to be gaining significantly more return on your dollars because of a longer life road. So your life cycle costs are going to be significantly less. And I mentioned how important it is for that pavement assessment, that pavement strength evaluation to be done up front to really understand what condition the road is going in. We talked a little bit about the mix design and performance tests that are done to assure that you've got the right binder being used. This is really looking at the pavement structure and whether or not you need to add additional structure to that pavement and what your process will do in regards to adding that additional structure for the loading that's going to occur. And typically you need to look out 20 years on what you anticipate the loading to be, because loading oftentimes goes up significantly over time. A lot of opportunities to use non-destructive test methods. We mentioned the falling weight deflectometer. We mentioned ground penetrating radar. One of the things that I think is underutilized is the dynamic cone penetrometer, because that allows you to go through a core hole and actually measure the strength of the underlying base and subgrade material at depth, just kind of looking at how far that penetrometer penetrates into the material based on the number of blows that are applied. So you get a really good look at the overall strength of that underlying material at depth. And then there's also destructive testing methods that include soil borings, coring, test pits, probe holes, and similar things like that. So that takes us to polling question number 3. What performance measures have you used to evaluate stabilized products in your agency or the area that you're supplying material or you're constructing in? What performance measures have you used to evaluate your stabilization products? It's a little harder because you got to fill in the blank. It's not a yes or no. Okay, I don't know if there's a problem here with getting answers posted, or if there just isn't any answers coming through, but I will move on to the next slide.
Hey, Dan, you should be able to see some of the answers here.
They're not coming up on my screen for some reason, Jason.
No.
So maybe you can read them off if you
Sure,
could.
I could do that. Here are a few. I don't recall that we use stabilizing products in our state. Reflected cracking, Marshall testing, roughness, Proctor, compaction density, unconfined compressive strength, FWD, or visible results over time, coring, DCP or FWD, distress surveys, visual surveys, visualizations. Got a variety of them.
Yeah, that's good. That means that people are doing their homework up front, and I can tell you that the little bit of money and resources that you spend on that upfront work pays huge dividends. It can save you from a failure and a huge problem project, and it can also save you a lot of money, both in defining, the thicknesses, how the material is going to be applied, and picking out which process that you're going to utilize. And we'll talk about that further as we go into our last topic here, which is why, in my opinion, the best rehab binder option, when it's viable, is engineered emulsion. And the main reason for that is that there's an awful lot of research work and performance data and performance evaluations that have been done over the last 20 years, and they point very strongly towards that being the best performing binder by far. And so before we get to that, I wanted to mention this little guide. It was done through research through the Local Road Research Board here in Minnesota. And it's a base stabilization guidance and additive selection for pavement design and rehabilitation. This was done in 2017, and it's a good reference that gets into a lot more details in terms of selecting the proper binder for your particular roadway, understanding what materials you're going to be stabilizing, and whether or not an engineered emulsion is viable for your particular project. And so I encourage you to utilize this resource, as it kind of pulls together a lot of good information. And then another great resource that you can use is the roadresource.org, the comprehensive resource for optimizing network management. I went to a super user group meeting and got to look at this tool in depth, and it really does a lot in terms of selecting from a wide variety of rehab options, and then utilizing both economic, environmental, and engineering application selection processes for making sure you utilize the right one. And it allows you to go through some really good tools to make that determination. Just to give you a quick overview of that, here is kind of one of the slides that you get to, and you've got all your different surface treatment and pavement rehabilitation options on the left. You can either put in your pavement condition rating that you have for the roadway, whether it be PCI or some other index, or you can select from a variety of photos of surface distresses that will take you to the right options or applications of these different recycling or surface treatment activities. And as you can see here, a road from A to D goes through kind of a deterioration process as the road ages and loses its life. So you really need to look at where your road is in that life cycle, or that spectrum of distresses, and then be able to select the proper treatment for that roadway accordingly. So you can get on there and take a look at that at roadresearch.org, and make sure you give yourself at least 45 minutes to an hour, because you can really click on a lot of things and see a lot of opportunities to utilize that tool. And now I'm going to get into some of the research that was done out at Minroad, and I'll give you a little bit of background on the Minroad facility and where the engineered emulsion was applied on that facility and the performance that has been seen over time. And so Minroad research site is on I-94, Interstate 94, and it comprises of a Minroad low-volume road. You can see that loop just to the right of the highway, where they've got a loaded truck that drives around that all day long and imparts easels or loading onto the roadway so they can do their evaluations for kind of local government agencies to look at applications for lower volume roads. And then you've got the main line, which is live Interstate 94 traffic. And you can see by the star there that that facility is located about halfway between the Twin Cities and St. Cloud, which is a good-sized municipal area. And 94 heads all the way up to Fargo, North Dakota, and then heads west from there across North Dakota. But a large amount of traffic goes over that roadway, and what they do is they divert the traffic from the main line to the test facility so that the vast majority of the year the traffic is on this test facility, and they can evaluate the traffic loading with the different test sections that they have in order to understand better what different pavement processes will do. They have both asphalt and concrete test sections. You can see here that you've got your westbound section going towards St. Cloud and Fargo, and then you've got your eastbound roadway, and then you've got the diverted westbound research section where the traffic is running on most of the year. The only time they divert traffic back to the old westbound section is when they're going to be going out to be either doing some maintenance, some construction, or to do their research evaluations. And then that road is comprised of all these different cells, as you see here on the lower mainline graphic, and that all these different cells basically are concrete research sections or asphalt research sections. And the engineered emulsion sections I'm going to talk to you about right now are cells 2, 3, and 4, which are on the west, towards the west end of the project there at Minroad. So what was done out there is to really look at the application of base stabilization on a high volume, high loading road, because prior to this, a lot of the state agency folks, NINDOT folks, were not convinced that this was a viable rehab application for heavily loaded interstate highways or trunk highways, that it was more fitted for county roads. And so SEM Materials at the time wanted to show that it is an applicable process for higher volume, higher loaded roads. And so they actually, SEM Materials paid for these 3 test cells and was in charge of not only the construction of this test cells, but also the pavement design and the material aspects of it as well. And so what came out of that was cell 2 was 50% wrap, 50% underlying base, which was the typical material ratio at the time. It was 6-inch stabilization of that material using an engineered emulsion at a 4% application rate. And then cell 3 was a 75% wrap to 25% underlying base. And you can come to these different wrap to base ratios just by either raising or lowering your reclaimer in that pulverization process prior to injecting your binder into the material. It's typically a 2-step process where you go in and grind up the material first and then come back with an injection of the binder into that ground up material. And so cell 3 went to a 75% wrap, 25% base. It was also stabilized at 6 inches, but reduced the emulsion added to 3% because of the higher wrap content. And then cell 4 was completely milled up and removed, and then the underlying base subgrade material, this was a full depth section, so it had a clay subgrade underneath. That was stabilized with fly ash, and then the millings were brought back and recompacted on top of that stabilized base, and the top 8 inches of those millings were stabilized at only 0.075% emulsion, so you can see that much less emulsion was used in this 100% stabilized material. And then there's also a section done on the shoulder. But here you see kind of how the differences between the stabilized sections were as related to the percent wrap and the amount of emulsion added. And so when you look at one slide that I neglected to put in here is what was put on top of that. And the overlay on top of those cells was basically a 2 3/4 inch hot mix overlay on Interstate 94. So you look at what an Interstate 94 typically would probably have 6 to 8 inches of hot mix on it for the traffic loading. Here they're only putting 2 3/4 to 3 inches of hot mix on top. It was basically 2 inches of super pave hot mix with a 3/4 to 1 inch bonded wearing course, which in some cases people would recognize the term Nova Chip. That was kind of the brand name of the time, but it was a bonded wearing course put over the top of the 3 cells. And so looking at the life of that, cell 2, 3, and 4, you can see here they've got the accumulated easels on that min road test cell sections. And from 2010 to 2016, you can see that the cumulative easels went from just over 1 million easels all the way up to 6 million easels. And one thing I should mention is that this was originally a 5-year accelerated testing evaluation. So the material was designed to last, the 5 years, and they expected over that 5-year time frame for the traffic to be about 3.5 million easels. So from that 2008 to 2013 was the 5-year time frame, and that's about what they had, as close to that 3.5 million easels. But because the roadway basically had no cracking, no distresses whatsoever, they elected to leave that go. And in this slide, it shows that the traffic level has doubled and still performing extremely well. And I can give you an update now to 2020 that the cells are still in place after 12 years of traffic loading, and there's still very little distress on those cells. They were recently cored because some people had concern about whether or not the engineered emulsion would maintain the underlying base material in a bound state. And I can tell you that the pictures of the cores and how those cores came out were extremely good. They all looked very good. And so this was really kind of a great representation of some really in-depth research that was done out at Minroad and a private company that helped put this in place. And they're still using a lot of research now to move forward. And I'll talk a little bit about that now in terms of fatigue theory. And when you look at perpetual pavement fatigue theory, it's basically looking at the loading that you're putting on the roadway. And as we all know, when a load is put on the roadway with an asphalt pavement, it deflects under that loading. And so the fatigue theory means that if you get a high strain, which the strain of the load being imparted on that bound material always goes to the bottom of the bound layer. So a very heavy loading is going to put a high strain at the bottom of that bound layer, and that's going to result in a shorter life of that roadway because it's going to cause a distress to occur quicker, and that distress is going to become many distresses over a shorter period of time. So the idea of you have a lower strain, you get a longer life is kind of the fundamental fatigue theory behind the perpetual pavement. So now if we look at the fatigue endurance limit, and this is tied to the perpetual pavement theory, and for those of you that are not familiar with perpetual pavement theory, it's basically putting a road design in place that has a sacrificial wearing course on top of a very stiff pavement structure that is on top of a flexible fatigue-resistant base material. And so the idea here is that if you can get those strain levels down to a lower enough level that you would get unlimited fatigue life on that road as it relates to loading. Not as it relates to low temperature cracking or weather related, but as it relates to loading from the bottom up stresses that occur. And so a lot of research was done for perpetual pavements, and for the most part that microstrain value that they came up with is somewhere between 100 and 200 microstrains is at the level where you can see that that fatigue endurance limit concept kicks in and you can reach that unlimited fatigue life. So here's a picture of what we're talking about. And the reason that we can have this picture is because they placed strain gauges out on those test cells when they were constructed. So they could actually measure the strains in the roadway and measure them over the life of the test cells. So you can see there on the left, you've got the bitumen or the engineered emulsion stabilized base, and that maximum tensile strain has been transferred down to the bottom of that material because it's a bound material. And in turn, what that did is significantly reduce the tensile strain at the bottom of the overlay, the 2 3/4 to 3 inch overlay, which then resulted in more of that whole concept of perpetual pavement to avoid having those cracking and distresses occur in that overlay. So that really explains to a great degree why you're seeing overlays perform so much better with cracking delayed for such a long period of time as compared to milling overlays, is that you're providing more of a bound base to that material. And you can see here on the right here, they plotted the HMA microstrains and the FFDR microstrains, and you can see that the HMA microstrains are all under 100 and the FFDR are all under 200. So it really fits that research that was done. Thank you, Jason. I had that when we tried I don't have the green arrow for some reason to be able to do that myself. But it basically shows those strains. And then looking at some additional research that was done by University of Arkansas, Arizona State University, and AAPT, really looking at how cracks originate and form, and how that relates to the material that they're originating and forming in. And it starts with initiation, where you've got microscopic defects and incompatibilities which are amplified when you apply stresses, and microcracks form. Kind of hard to see, but you can see the little red microcracks within that specimen there. And then continuing on to the right side of the picture, you've got crack initiation, which we just mentioned kind of turns into coalescence, where those microcracks grow and coalesce into macro cracks. And then once they become macro cracks, they propagate, and that's when they move through the material and become a crack at the surface. And that would be how a load-related crack initiates at the bottom, moves through the material, and creates a crack at the surface. So what we found is not only by moving those maximum tensile stresses to the bottom of the bound layer, but the ability of these recycled materials to keep the cracks from coalescing and propagating is still not completely understood, but it would be a good topic for a PhD student to do his thesis on, I think, because I think it's a combination of the unaged binder that's being used in those processes, along with the voids of the cold-in-place materials, because cold-in-place materials have higher voids than hot mix. Typically, you're looking at 10 to 15% voids as compared to 6 to 8% voids. And I think the the whole concept of a crack being able to form and move through that void structure in combination with an unaged asphalt is really key to the ability to withstand that load-related cracking. And so that really gives you an indication of why engineered emulsions perform so well. So some final thoughts. In my opinion, by far the most researched and developed material used in recycling is engineered emulsions. The mixed design procedure is in place for material selection. The specifications are there and criteria for performance tests which address strength, durability, crack resistance, and that balance between strength and stiffness, which addresses flexibility and fatigue resistance. It is, again, in my opinion, provides the best long-term performance and best life cycle value, with the caveat that you've got to use it when it's a viable alternative. So that means doing your homework up front, understanding the materials that you're stabilizing, and applying it appropriately. And then successful implementation, for those of you that have not started to utilize and benefit from engineered emulsion, is to find a statewide implementation champion. That's been the case for most states. Create technical teams with reps from each district that you're going to be trying the products out in. Establish performance measures and initiate that performance tracking, whether it be your pavement management system or doing it more informally with windshield surveys and crack measurements and that type of thing. And then make sure you get a commitment from management and industry in order to make sure that it goes forward in the proper way. So our last polling question now is, how many other stabilization products have you used and what have been their results? And Jason, I don't think I'm getting the answers, so if you could read those off once we get them, I would appreciate it. Oh, here, it looks like I got it this time. Nope, disappeared again.
I just got it up there for folks to start responding, so
okay.
Give us a few minutes. Got a few responses. No experience yet. Engineering emulsions. Not applicable. And then asphalt, emulsion, foamed asphalt. Cement foamed. Lime Portland cement result in a kind of a rigid base. Only emulsions. Getting some good results here.
Okay, well, good.
Fly ash may be the base of a bit too strong. Has it acted? Emulsion grade experience. Foamed asphalt. Typically,
I hope for those folks that have not had experience with engineered emulsions, I hope that this presentation has provided you with information that will allow you to at least try the product and then evaluate it in conjunction with your rehabilitation approaches that you're utilizing now. And for those of you that want additional information, there's some helpful links that you can get. That first link there is that guidebook that I mentioned earlier that helps you define what additive to select in terms of your pavement design and rehabilitation. The FHWA has significantly unlimited information. This one provides their checklist series on pavement preservation, which cold-in-place recycling is part of. The Pavement Preservation and Recycling Alliance, we talked a little bit about roadresource.org, and that is really a great tool to help in the selection process, and the National Center for Pavement Preservation, pavementpreservation.org. So I encourage you to check all those out. And I think we've got just about the right amount of time for questions, if there are any.
Dan. I'll read out the questions if you want to answer them, Dan.
Okay.
Scott Dimitrov had a question. How do we get the survey questions off the screen once we answer them? Well, I will provide those responses for the survey questions when I send out the presentation material. So you guys will either get it tonight or tomorrow. Stay tuned. Good question, Scott. Jim, need to remove survey questions off the screen. Okay. Well, Jim, we did our best. John Arambari, sorry if I pronounce your name. Survey questions are stuck even though they're closed. Never mind. Okay. Let's get some real questions here. Gentleman Wilson from Puerto Rico, what will be the optimum temperature for storage CFS 1HP emulsion?
Follow your manufacturer's recommendations. That's all I can tell you because, you know, when you're talking about polymer modified materials, the manufacturer is going to provide you with the best recommendations on material handling, and I can't give you an answer that might send you down the wrong path. So I definitely would visit with your supplier and the material manufacturer for those recommendations.
And a question from Mark Eden. Anti-strip provides a better adhesion, question mark.
Yeah, that's one of the benefits of emulsions is that most of them have anti-strip characteristics that do provide better adhesion to the aggregate, and you know, even when you're using them for tack material, it can help in the adhesion there too.
Hey Dan, how about foam?
How about foam? Adhesion?
Provide a better adhesion?
Yeah, like I said, you're getting good coating on the fine aggregate. And those are going to hold your coarse aggregate in place. So anything you can do to provide better adhesion on that fine aggregate is going to benefit your overall performance. So yeah, I think depending on your aggregates, especially with stripping prone aggregates, any type of anti-strip is preferable.
All right, Dan, we've got another one from Alan. Please elaborate on the surface chemistry means of getting the water out.
Oh boy, you know, I'm more of a field guy than a chemistry guy. I mentioned Peter Schilling and Bill Gruba, but they call it a chemical cure, where the chemistry of the surfactant and the agent, the chemical that goes into the process, actually helps drive out that moisture. And how that mechanism works, I can't tell you, but I would encourage you to visit with some of the people I mentioned earlier.
Okay, we had another question by William from Puerto Rico. How a small emulsion producer can assure PG's quality are in compliance? Any recommendations?
You need to test it, so you'll have to send it out to a testing lab. If you're looking at the base A CPG criteria before emulsification takes place, I know that the user-producer groups are coming up with more quality control tests for the emulsion itself, and there will be more testing that's going to be required for that. So if you're a small emulsion supplier, I would encourage you to either look at getting up to speed on some of these new tests that are going to be coming down the pipe, or find yourself a good, reliable testing firm that can do that for you. West Test in Colorado is a phenomenal testing firm. There's a number of them that you can get access to.
Okay, Dan, got a few more while we got 5 more minutes left. Scott Demetro, did they do any FWD testing on any of the sites before or after on those case studies, as you mentioned?
No, they did not. Unfortunately, they did not have any FWD testing done on those.
I want to reference to everybody, as of last Monday, there was an MCHRP 962 that just was put out. It was called for rapid test and specifications for construction of asphalt treated cold recycling pavements. So it may not be out there right away, but in time as MCHRP gets these reports out, please search that and get some good information there.
I did see, Jason, a question. Now that I reduced my screen, I am able to see some of the chat questions. I saw a question about a lightweight deflectometer and how well they are. They certainly are not as accurate as a full depth, a big FWD piece of equipment is, because it doesn't have the multiple geophones providing those deflection basin results back to the computer. But they can provide some good spot location information, and I think for what we're talking about here, which is recycling, they can be a good tool to use.
I know, Dan, in national parks, when we had recycling projects, we had the automated manual one that was like a Marshall machine where you just let it go back and forth, and we got readings from there. So just another good tool.
Yeah. Yep. And I think I saw another one about cement, but it was about defining how much cement and make sure you're not getting it too stiff. And I typically am between 200 to 400 psi confined compressive strength, and that is going to be based on your traffic loading and whether you're at the high end of that or the low end of that.
There's a gentleman named Jim. What are your thoughts on Reclamite and BioRestor?
There's a lot of rejuvenating agents that are out there now that can really put the, is it the maltines? I guess the maltines back into your asphalt to provide the attributes that you're looking for. I would encourage you to access NRRA, the National Road Research Alliance, and that's multiple states that went together to do a lot of research, and they've got a research topic right now on rejuvenating agents, and they've actually done quite a bit of work and have some results that they could share with you. So if you go to National Road Research Alliance and contact somebody there, they can provide you with the data that they have.
Dan, with the few minutes that we have left, I want to give Allie or Ann a chance to mention our upcoming next month's webinar. Ann or Allie?
Thanks, Jason. We just wanted to say thank you again to both Dan and Jason for the participation today on this webinar. As you can see on the screen, our next webinar is scheduled for August 20th at 2 p.m. Eastern Time. It'll be on chip seal, introduction, site selection, design, and materials. You can register at the link that's provided on that slide. We will also be sending out the registration link in our email with a copy of this recording. Again, we thank Jason and Dan.
You're so welcome, Allie and Ann. Now, while we got like 1 minute left, I ask each to the presentation material as well as the flyer for upcoming and past webinars are on the file share. Please feel free to download. And also please take the time to go through the evaluations. On the evaluations, use the smaller of the arrow below the play to advance to the next page. There's like 5 pages. We appreciate any feedback you can provide us. This will assist us in providing better webinars for you, and that's what we're all trying to do. So, Dan, any further final comments?
No, thank you for the opportunity, and I appreciate all those that attended and that hung with me through this hour and a half.
For those of the questions that we weren't able to answer, in the next day or two, we'll respond back accordingly on an attachment, and we'll get those questions back to everybody for their information. So with that said, we really want to appreciate your time participating today, and we look forward to your participation next month.
Thank you, Jason.
You're welcome. Thank you, Dan.
That concludes our webinar for today. Thank you for your participation for using AT&T teleconference service. You may now disconnect.